proof video for the course Math 156 at Harvard Extension School. In this video, we are going to prove that first, that the variance of x is equal to the expected value of x squared minus the expected value of x squared. And then second, we're going to prove that the variance of a constant times x plus another constant equals a squared times the variance of x. And then lastly, we're going to prove that the variance of x1 plus x2 equals the variance of x1 plus the variance of x2 if x1 and x2 are independent. So let's start with our first thing to prove. So by definition, the variance of x equals the expected value of x minus the expected value of x squared. And if we take this quadratic term here and expand it using the binomial formulas, we get x squared minus 2 times x times the expected value of x plus the expected value of x squared. The next thing we're going to do is we take the single parts because we can do that by linearity of the expected value. So we take the expected value of x squared, subtract the expected value of this guy over here, which simplifies to minus 2 times the expected value of x times the expected value of x, because what we get here is that the expected value of the expected value of x is still the expected value of x, because the expected value of a constant is still a constant, plus same thing here again. In the last term, we take here the expected value of x squared, which is still the expected value of x squared. If we sum all of this up, we get that the expected value of x squared minus the expected value of x squared, like the whole thing squared, and then this is exactly what we wanted to prove. And then the next step, we're going to prove that the variance of a times x plus b equals a squared times the variance of x. So what we get here is that we basically just plugged in our first thing we proved here. We plugged in ax plus b. So we get the expected value of ax plus b squared from here, minus the expected value of a times x plus b squared, which is this here. And for x, we basically we plugged in ax plus b. And then if we again expand this one using the binomial formulas, we get that it's the expected value of a squared times x squared plus 2 times a times b times x squared plus b squared. And we left this one just the same as in the first step. And then we do the same thing we did in the second step here. So by linearity of e of x, of like the expected value, we get that we take the expected value of the first term, so the expected value of a squared times x squared, which simplifies to a squared times the expected value of x squared, because a squared is a constant, and the expected value of a constant is still a constant. And we do the same thing with the last two terms. So here we have plus 2 times a times b times e of x, the expected value of x, because a and b are both constants, and so is 2, so we can put this in front of the expected value. And then plus b squared, again, the expected value of a constant is still a constant, so we're left with b squared here. And the second term, we did the exact same thing. We take the expected value of a times x, which is a times the expected value of x, because a is a constant, and then we follow the same logic here with b. And then we take all those terms together, and here the last part, this one, we extend again the binomial formulas, and we are left with a squared times the expected value of x squared minus a squared times the expected value of x squared, which, when we put the a squared in front of the terms and like put it in front of the brackets, we get a squared times times the expected value of x squared minus the expected value of x squared, which is, as we defined it in one, or proved in one, just the variance. And that's how we proved number 2. And lastly, we're going to prove that if we have two independent variables, x1 and x2, then the variance of the sum of x1 and x2 equals just the variance of the single terms. And here, again, in the first step, we use what we proved in number 1, this one, this here. We just plugged in for x1 plus x2. So we have the expected value of x1 plus x2 squared minus the expected value of x1 plus x2, and then the whole thing squared, which again we expand using the binomial formulas. And in the first term we are left with the expected value of x1 squared plus 2 times x1 x2 plus x2 squared minus the expected value of x1 plus x2 x1 plus the expected value of x2, and then that whole thing squared. And we expand that again making use of the linearity of the expected value. So we take the expected value of the first term, which is the expected value of x1 squared, plus the expected value of 2 times x1 times x2, where again we have 2 as a constant, so we put that in front of the brackets and are left with the expected value of x1 and x2 squared, and so on and so forth. And we are left with this huge formula here. I already rearranged the terms because we will see the next step. Now we have that this first part here. Oops. I'm not good at drawing. Glad that I took math and not art classes. So this first term here coincides with our definition of the variance for x1. The second term coincides with our definition of the variance for x2. And then we are left with those two terms. And for the last two terms, we have make use of the fact that the expected value of x1 times x2, so this here, is equal to the expected value of x1 times the expected value of x2 for independent variables. So this is what I did. Not here, but what I did here. So because x1 and x2 are by definition, in our case, independent, we can substitute the expected value of x1 times x2 with the expected value of x1 times the expected value of x2. And here the first two terms, I basically just plugged in the variance of x1, because what we said is that this is exactly the definition of the variance of x1. And what you can already see is that those last two terms cancel out, and we are left with the variance of x1 plus the variance of x2, which is what we want to prove. Thanks for listening.